Let's learn about neural networks. After this lesson, you will be able to code your own neural network from scratch. You will understand how this works, and you will be able to then further build it into projects and AI research, etc. Make sure to have PyTorch installed, NumPy, Matplotlib as well. You can find this repository at the GitHub below this video. So this is a neural network, but let's just first focus on a single neuron. So let's just look at this first blue circle and the first white circle and this output. And let's imagine none of these other exist. So input would be some number. And then it's multiplied with some weight. This weight is learned by the neural network. So this weight will also be some number. And when input is multiplied with this weight, it will give some output. So the output is gonna so the neural network will transform this input into output, will predict something. And the weight that's multiplying the input and transforming it into output is gonna be learned during training. So what is the best weight that's gonna give us correct output based on any input? That's how neural network learns and then generates or predicts. So let's check code example. Let's say we have inputs 2 and 3. And then these would be weights. These would be neural network weights like 0.5 and 0.3 that are learned, that are already learned. So we'll see later how they are learned. Now we could also have a bias. It's just a single number that's added for the entire layer, entire set of weights. Entire set of weights has a single bias number, and you see here the output, the weighted sum, it's gonna be this weight times this input plus this weight times this input, and then at the end we have some bias. So bias is also learned. It also helps, if you know functions, bias will help this function, whatever it is, to move left and right. And these weights are gonna determine the slope. So this is in my math course for machine learning that I published earlier. In this case, this is just a dot product. Right here is just a dot product between input and weights. And so weighted sum is 2 in this case. And then because this is gonna be some linear function, if we wanna make it maybe curved, we need to actually pass this through some activation function, for example sigmoid. Now when we pass this output, weighted sum, through some function like sigmoid, it looks kind of weird, but let's just ignore like whites like this. Let's just imagine that sigmoid is gonna make this function like curved. So if you have some data points here, you wanna actually separate them with a curved function. If you have a straight line, then it will not separate these like messy data points. So you need to be able to curve the function to separate the data points. That's what activation function will do. It will take this weighted sum, which is a line, and make it curved. And so at the end, for these specific numbers, we get this activation or output. So this here is sigmoid function. We also have other activation functions like ReLU, and their purpose in neural networks is to curve the lines that are, because lines we get with just multiplying weights and that bias are straight lines. Because here, let's say we want to separate maybe this red data set. We cannot do it with a straight line because it can just like cross over it. We need a curved line that goes around this like this. So that's why we have activation functions to curve the lines. So that's how neural network will be able to learn how to separate these datasets. But let's see on some examples more. Join my school community to become AI researcher, link below, or you can find link on my channel here in the about section. So usually you would first initialize a neuron. So weights would be initialized as random numbers from a normal distribution. I explained that in previous PyTorch lesson on my channel. And then make it very small. So maybe these would be around like 0 to 1, a bit more maybe. But we will make them all very small, so they're around 0.1. Bias goes at 0 because bias is being added. So in the beginning we add 0. But you don't want to initialize weights at 0 because weights are multiplying. So whatever, then they will just turn everything to 0. So that's not good. You want to initialize weight with some number. And here we would instantiate this class, neuron, and let's say number of inputs is equal to 2. So then this will create 2 weights and 1 bias. So this number of inputs just influence the amount of weights. So this is example. Number of inputs 2, and these are the random weights that we generated. They're really very small because we multiply with 0.1. So then to our neuron class we want to add this weighted sum function. So it will take inputs, the numbers. So this is different from number of inputs. This is the inputs, the actual inputs numbers, and this will do dot product between weights and inputs. Now this is also matrix multiplication. It says here dot, it's a bit confusingly named, but this is matrix multiplication between weights and inputs, and then add bias at the end. And then we're also going to add this part to our code. So after we initialize, we already seen this part of initialization. We want to add this part. So I set some inputs here, and then I call neuron.weightedSum. I call our new function to do matrix multiplication. So the weighted sum here is 2, which also includes this bias, by the way. Now we will add a third function to our neuron class, which is going to be this sigmoid function. And so it makes it non-linear, so it curves our line, because when we just multiply with inputs with weights and that bias, it's going to be a straight line. The function is going to be a straight line, the function of weights times inputs plus bias. But sigmoid makes it curved, or activation function makes it curved, and we will use sigmoid because it has like a nice curvy shape that neural network can use well. So this is the formula for the sigmoid function. We need to pass in this number, and then the formula is 1 over 1 plus e2 minus x. And then we will just pass our activation, or I should say the output of the weighted sum, through sigmoid, and we will get some activation value. Sigmoid will be between 0 and 1 like this. It's gonna be curved, so if neural network needs to make this maybe left curve, it will make weights and biases such that we get some number around -2 and -1 or something like that. And then after activation, it will get this left curve to maybe encircle some data. If it needs this other right curve, then it will learn its weights and biases to give a number around 1, 2. So it will get this curve here to encircle some other data in this way. So this activation function will never change. It's just the weights and biases. But then neural network will learn to adjust weights and biases, so when the output is passed through activation function, they will properly encircle data or be able to predict or generate data. That is, it will have proper understanding of the data. Now we can test this with different inputs, So 0, 0, 1, 0, 2, 3, and you will see that the output is always some number between 0 and 1. We can also try different activation functions. So sigmoid will give 0.8, ReLU will give 2, this tanh will give 0.96. So depending on the activation function, you need to find one that works well for your dataset. For example, ReLU is very easy and fast to compute, but it's not as powerful. So maybe if you need some quick and easy task. Now let's see how to combine multiple of these neurons, not just one, into a neural network layer. So again, we will have input 2, 3, let's say, but then we will have two neurons. The first neuron is this one, 0.5, 0.3, and the second neuron is 0.2, 0.4. So you see that it has weights for each of the inputs. And we will have two biases, so one for each of the neurons. And the forward pass is the matrix multiplication between inputs and weights transposed. So I explain matrix multiplication in math and PyTorch fundamentals, but you can also check how it works, but you need to transpose weights here. Now, some people can also write like weights matrix multiply inputs or inputs transpose. Now this just depends on how you save your weights in memory. You know that matrix multiplication, there are some rules. But for now, let's just take it as is. So inputs at weights transpose plus biases. So we have input tensor at weights transposed. At the end, we get this output, 2, 1.8. And then if we pass it through sigmoid activation, each of them will be some number between 0 and 1, depending on the input here. So here we would define a class layer, and then it would have number of inputs and number of neurons. So these are like hidden neurons. It can be different number. You see here we have 3 inputs, but 5 neurons. 5 hidden neurons, I should say. And then 1 output at the end. So in our linear layer that we initialize, we have number of inputs and number of neurons. And weights are gonna be number of neurons, comma number of inputs. This is one of those weird things that you just need to kind of get the intuition by trying and understanding. So number of neurons is 3, means we have 3 rows. 1, 2, 3 rows. And number of inputs is 2. And that's the second dimension here. So we have 2 columns. So in each row there is 2. So 2, 2, 2. So 3 rows, 2 columns. And that's why we also need to transpose, because we have 2 inputs. We need to transpose this matrix. So because of matrix multiplication, we will multiply these 2 and these 2, and then these 2, these 2, these 2, these 2. So we need to transpose, flip the matrix of weights. But I recommend you just try to understand this yourself, or you try like playing around, see what happens, try to draw. Understand how matrix multiplication works first. You need to practice this. These are the example weights that are initialized. And the input is 2. So when you multiply input matrix and weights matrix, you need to transpose this, because you are multiplying a row of the input with the column of the weights. So you want to multiply it with this row, but you cannot multiply row and row. So you need to transpose this row to become a column. So now it's just 2, 2, 2, like this. So then after initialization, we will add this weighted sum. And here we just do inputs, matrix multiply weights transposed. We need to transpose them as I explained, plus biases. And at the end, you will get something like this. We will get 3 numbers, because the hidden number of neurons is 3. You know, we are multiplying 1 times 2 matrix of inputs times 2 times 3 matrix of weights. So the result will be 1 times 3. So this is matrix multiplication. So you have these 3 neurons that you get as a result. So again, I recommend you try this out yourself, change some numbers, try to understand how this matrix multiplication works. And then it's very easy to add this activation function. So torch.sigmoid and pass in the neurons. So before the activation, the numbers that we got of the neurons are these, and then after activation, it's gonna be this tensor or vector. So after we have this sigmoid, we would add that to this forward function. So in the forward function, we first do inputs times weights plus biases, and then pass the result through sigmoid activation, and then that's the output. Those are the neurons that we get. And so we can say output is equal to layer.forward and pass in inputs. This is how you would usually do it in neural networks, large language models, reinforcement learning, everywhere. Here we can take a look at some activation functions. So I already explained sigmoid. It puts any value on x between 0 and 1. Output is always between 0 and 1. We also have relu. This is very easy and quick to compute. So if the input is lower than 0 or 0, it will just become 0. The output will just become 0. And if the input is larger than 0, it will just remain that same number, whatever it is. So r of z is our number, is going to be maximum between 0 and z. So that's the relu function. You just find set 0 or z, whichever is bigger. This is very fast to compute. You would use this if you need some quick computation that's not so maybe powerful or precise, but you just need some easy task for the neural network, and maybe it can do it with this activation function. And you see here, it would just, if you have a line, it will maybe make that line like this. It's not going to be curved. It's going to be like this, just like cut or broken like this. But it will be a continuous line. It will not be like separated. But for some tasks, it's not good if you make outputs that are lower than zero, exactly zero always, so you kind of erase all of that information. So there is a leaky ReLU. So outputs that are lower than zero, it will just make them a lot closer to zero, but not zero. So it will just squish them towards zero, but they will still not be zero. So they will be 0.1 times x if they are lower than zero, or they will just remain x if they are higher than zero. So this doesn't erase completely information like the ReLU function, while it still provides nonlinearity, this bending. So the neural network can use this bending to encircle some data. Here we have some examples. You see, this is the zero. So ReLU is just zero. And then GeLU is actually more curved around zero here. So it preserves information if the number is around -2. So, and then we have ELU that's kind of going down even more. So we have these different activations. You would test which ones work best for your data. Here is another example: Sigmoid, ReLU, SILU, Swish, ELU. They're all kind of similar, but they do a bit different things. But they will all curve your line of weights and outputs and neurons. You see, with just multiplying weights and inputs and biases, you would get a straight line, but then passing that through activation function, you would get a curvy line. This is a good example as well. You want to fit this data with a straight line. It's going to be tough. You're going to have to leave out a bunch of this red data on the other side, which is wrong. But with a curvy line, maybe this is a sigmoid function here, you can fit data properly. Now, to understand how neural networks learn, I have 3 good videos. So you can watch this one, backpropagation from scratch, torch.backward, and this one where I train a neural network. I'm gonna leave all these links in the description, or you can just search for them. I also put these 3 videos here in the 3rd lesson after these neural network and layer and stuff, so you can just copy these URLs. That's gonna be it for this video, and see you in the next one.